Thank you.
Okay. Okay, so just we will focus again on the soft Adriatic, but on the chemistry part, so on the carbonate system. So I will give you, even if we all know about the carbon cycle and the ocean acidification, a really brief background. Then the acidification in the Mediterranean Sea, just for who is not familiar with the area. The Adriatic Sea, I will almost skip it because we already spoke about it a lot, about the role of the dense water formation. Then I will focus on the carbonate system in the South Adriatic, so in the water masses that characterize the area, and then the temporal variability of the carbonate system in this masses. So the carbon cycle, as we all know, since the industrial revolution, the carbon dioxide, CO2 in the atmosphere has grown. And this is for the fossil fuel emissions and the industries, but also for the land use, like the deforestation. And there are two sinks of CO2. One is the land, but the biggest one is not the biggest, but the other one that is important for us is the ocean. And since the Industrial Revolution, almost the 50% of the CO2, anthropogenic CO2, has been taken by the oceans. I think that most everybody knows this graph. This is the longest time series for CO2, atmospheric CO2 record that is in the OA. So it's in a site that is not influenced by the land. So it's really a good site, let's say. And it's really long because it starts from the 50s, 1950s. And we know that in 2015 we passed the 400 threshold, and that this increase is the highest that we have found in that small period. So this is a reconstruction from the Antarctic ice cores. So for CO2 in the atmosphere, we have a long time series. For PCO2 and pH, the time series is much smaller. In Hawaii, they started to measure it at the end of the 80s. And we can see that the PCO2 in seawater has the same trend of the CO2 in the atmosphere, and the pH has the opposite trend, so it's decreasing. In the Mediterranean Sea, we have one observing site that it's in the south of Italy. The time series is much smaller, so it started in 2007. But anyway, we can see the same trend that is recording away. Speaking of the Mediterranean Sea, it is a concentration basin. We already said it, that the salinity is really high in the eastern part of the Mediterranean, and also the total alkalinity at surface is really high. If we compare the Mediterranean to the Atlantic, we can see that our surface salinity is 39.1 compared to 36.8. The alkalinity is 200 micromoles per kilo higher, and even the total disorder in organic carbon is 100 micromoles higher, and pH is higher both at surface and at deep. Speaking of the ocean acidification, in the Mediterranean Sea, we had the longest time series in the Gulf of Lion in Villefranche, and they record an acidification trend at surface and at 50 meters of 3 parts per thousand. it's even bigger than the one that we find in the oceans. Even in the Adriatic Sea, we have a time series, but it's too short to speak of acidification trend at this moment, so we have to wait to have more data to speak about it. But we can anyway see the trend of acidification even here. So, okay, we already spoke about the dense water forming in the North Adriatic and what happens when they go down in the South Adriatic. And even this picture, you already saw it, but just to remember it, the North Adriatic is a sink of CO2. So it's absorbing CO2 from the atmosphere. We have two observing systems of the carbonate system. One is, as you already know, the more in the South Adriatic, and the other one is here in the North Adriatic, in the Miramare marine protected area. But we do not only have the sensors that are measuring continuously, we also do cruises, as Pepe said this morning. So we had 8 cruises from 2000 to 2017. Unfortunately, we didn't have all the transit for all the cruises because half of it is in Croatian waters, and so we do not always have the permission to go there. Yeah. So 4 of them are complete and 4 are just half of the transit. And we took samples for dissolved oxygen, pH, total alkalinity, inorganic nutrients, and total dissolved nitrogen and phosphorus. These samples were analyzed. The dissolved oxygen was analyzed by the Winkler titration on board always, while the total alkalinity has been measured always in the lab here, always with a potentiometric titration. pH was measured sometimes on the boat and sometimes in the lab with a spectrophotometric measure, and inorganic nutrients were measured always in the lab with the autoanalyzer. For dissolved oxygen, we have a precision of 0.2 micromoles per liter. For total alkalinity of 2.8, an accuracy of 2.8 micromoles per kilo, and for pH 0.005 pH units, and those two are really important. The accuracy of the carbonate system measures, it's really important because we need to find, as I said before, a change that it's really, really small. I mean, 3 parts per 1,000 for here, so it's really, really small, and you need to be really accurate and precise. And for nutrients, precision and accuracy depend on the parameter, but are more or less between. The precision is between 0.001 and 0.012 micromoles per liter. To check the accuracy, we use certified reference material for total alkalinity and for pH. And we participated to international intercalibrations that are done by the Scripps Institute of Oceanography of Andrew Dixon. And to quasi-meme, that I didn't try, twice a year for inorganic nutrients, and to, I don't know how to say YAMSTEC, I don't know how to pronounce it actually, that it's an intercalibration organized by Japan for nutrient analysis. So thanks to total alkalinity, pH, and inorganic nutrients, salinity, pressure, and temperature, we were able to calculate the other parameters of the carbonate system with the CO2 software, that it's a free software, pretty easy to use. And regarding oxygen, we calculated the apparent oxygen utilization to eliminate, let's say, the temperature effect and to have just the biological effect of the change in the oxygen. I don't know if you are familiar with this parameter, but it's the difference between the oxygen concentration at saturation equilibrium and the measured oxygen. So if it is under 0, so if it's negative, the environment is supersaturated. If it's 0, it's saturated, and if it's higher than 0, it's undersaturated. Okay, then speaking of the water masses that we found, there is an error, between 2013 and 2017, we recognized the eastern South Adriatic surface water that is characterized by high salinity, a depth lower than 50 meters, and the apparent oxygen utilization. What? That is almost 0. And but we didn't have a lot of data, as I said, because we don't have the entire transect for all the cruises. Then we found the western South Adriatic surface water that has a low salinity. It's a little bit higher, so less than 20 meters, but it's always an apparent oxygen utilization almost equal to 0. The Levantine intermediate waters that are here, that has a salinity higher than 38.8, and a depth that is between 300 and 500 meters, sometimes even more, and an apparent oxygen utilization between 30 and 60 micromoles per kilo. I didn't say. And then the South Adriatic dense water that have a density higher, a potential density anomaly higher than 29.2, and are at a depth higher than 880 meters. In this case, we found these samples that are really weird, let's say, not weird, but different from the rest of our data set. In July 2017, they were surface samples with a really high salinity, with a really high alkalinity and low pH. So we still have to understand what exactly happened in 2017 in July.
It was very warm.
Yeah, maybe we can discuss about it.
It was very warm. One of the
it was really warm. Yeah, they were even warm. I think.
Yeah.
Yeah, really warm. You can see it because it's almost 25.
Yeah.
Okay, so speaking of the characteristic of the different water masses, those are the mean values for the apparent oxygen utilization in the different water masses in the different cruises. So all the surface waters, as we expect, as an apparent oxygen utilization concentration that it's almost 0 or under 0, so it's supersaturated or saturated, while the Levantine intermediate waters and the South Adriatic dense waters has an apparent oxygen utilization value that it's really high. And this can mean that those waters are older because the oxygen has been consumed a lot. This is the maximum value, so we think that maybe in 2016 the dense waters were not renewed, let's say. They stayed there and there was nothing new that could decrease the value. With total dissolved organic carbon, we see the same thing, more or less. So for dense waters, the value is really high because there is remineralization, while it's lower for the surface waters in the western part, and even in the eastern part, actually. In this case, we think that we found the Ionian surface water because the salinity was really high and total alkalinity and total dissolved inorganic carbon were low.
Why not the Levantine surface water?
Because it was just in the eastern part, just really, really eastern, coastal. Levantine goes even there.
Okay.
I thought it was a little bit more, not so coastal.
Okay.
But,
okay.
It's surface.
Yeah, but she said
Levantine
Levantine
surface water, I say.
Here we calculated the pH at a constant temperature to eliminate again the effect of temperature on pH. And we can see that the highest values are for the western surface waters, and the lowest are for the dense waters. Where are those? Those are transect. Two of the 4 cases that we had of the complete transect of the South Adriatic. This was in March 2014, and we can see that here the apparent oxygen utilization is high, but we cannot really, let's say, distinguish the dense water work from the other water masses. While with the PCO2, it's really clear this signal that it's we understood that it's from the Levantine intermediate water, and here where the PCO2 is again high is the dense water, and we have even the pH really low here and here, while those are the western surface water with high pH. 3 years later, more or less, we had another complete transect, and in this case, the Levantine water were all more homogeneous, let's say, in the transect. They covered all the transect and those. And at the bottom, again, we could see the dense waters really, really well with high PCO2 and low pH. And in the surface, we could see in both sides the surface waters. Okay, those are just regressions. In this graph is to show that the TCO2, so the total dissolved organic carbon, is really variable at surface where it's taken from the atmosphere, but it's really, really variable, so it depends on season, temperature, and a lot of variables, while going in the deep is more stable, let's say, yeah. And doing the regression between TCO2 and apparent oxygen utilization, we did it to check if our ratio was like the Redfield ratio, but we found a ratio that is lower from the one of Redfield, and we think that this is due to the fact that we do not have only a biological component in this. This is all the transect. So it's not just the deep water, just the surface water, it's all the transect and all the cruises. So different season and different environment, let's say. Comparing the pH at a constant temperature and the apparent oxygen utilization, we can see that there is a really nice regression, and this underlines the biological processes that has a really high influence on these two parameters. Looking at the nutrients, we did the regression between total nitrates plus nitrates and phosphorus for the Levantine intermediate water and for the dense waters, and our ratio in this case is more or less equal to the Redfield ratio. In this case, it's a little bit higher, and this can be due to maybe less phosphorus, but we still don't know. We still have to understand it. Looking at just one station of the transit, the central one that is represented more or less of the South Adriatic pit, let's say, we can see the temporal variability. That it's high. For pH, we can see the certification here. In this case, it's the one of July that, as we said before, was really high. The temperature, so pH at the constant temperature is really high. PCO2 is really high too, but and the salinity was really, really high. But that's the only sample that we have in summer. Here we can see probably the Levantine. It's deeper than in other cases. and here the dense waters. And here we can see that there is a remineralization by the how it's higher. Passing to the sensors, so not the discrete samples, but to the continuous monitoring, we have a time series from 2015 here of the measures of temperature and salinity. Even here we can see that salinity was really increasing this year in 2017. And here we have oxygen and pH, and those are the discrete measurements that agree really good with the measures of the sensors. And we can see the variability due to the changes in the temperature. So when the temperature is higher, so during summer, the pH and the oxygen are lower, and when the temperature is lower, pH and oxygen are higher. And a thing that we can see from this graph is that the variability is really high for those parameters, especially for pH. The seasonal variability is of 0.44 units. So it's really, really high. Even salinity is 1.22, 16 degrees of temperature. So it's the variability in the system is really, really high. This is more or less the same graph, but in this part we have oxygen and PCO2. So the trend of PCO2 is the opposite of oxygen. It's higher when the oxygen is low, so during summer, and it's lower when the oxygen is higher, that it's during winter. But as you can see, we don't have really continuous data because sometimes the sensors didn't work, and probably all this noise is due to the fouling on the sensors, because the maintenance of the instrument is not so easy because we cannot go on the buoy, as they said this morning, every month or every week, but once per year. So during a year on the sensor, there is a lot of fouling. And even in this case, the variation is really high, 210 microatmospheres. So to conclude, we saw that the South Adriatic is a remineralization basin, and in fact, the dense waters have high apparent oxygen utilization, the lowest pH, and the highest TCO2, while the western surface waters are the most productive with the lowest apparent oxygen utilization, the highest pH, and the lowest TCO2. Another thing that we want to underline is that the seasonal variation of the CO2 system is really high and is strongly driven by temperature. So it's really important to keep monitoring with discrete samples and with sensors to understand the changes due to the climate forcings. And one of the future tasks is to estimate the CO2 exchanges between air and sea at the air-sea interface. Oh, that's it.
Thank you very much. I have some questions. Yeah, some questions. I have one question. Can you go to the time series from the station? This one, yeah. So in this case, admit that I'm not so aware how the system is, the CO2 system works in this. Here we have been going to the to the station in different part of the years, especially during the winter time or the autumn, late autumn. We had just one in the summer, and now we have the other one in October, but it's still the same period, and it was already mixed and everything. So in this case, to analyze, is the seasonality influencing very much the first 200 meters, 300 meters, or how much you influence the whole water column?
More the
how much it can.
Yeah, I don't know exactly
Okay,
until
the higher influence is where you have the highest temperature variability. So of course
the
is
Yes.
in the upper part, which is under the seasonal warming.
For the
influence.
thermocline, yeah.
And also most of the biological influence is also in the photic zone, whereas the variability, the bottom variability is mainly linked to the residence time or to the history of the water that are filling the South Adriatic peak.
Okay, thank you. Other question? Someone has another question? No? Okay. Thank you very much, Silvia. The next presentation will be given by Elena Mauri. It's related to the gliders and its timeline variability from glider time series in the South Atlantic Sea.
Okay, I hope you are still awake and not too tired after all these long talks. So I left my title, the title wasn't on the agenda, but I added some more because after I listened yesterday to some talks, I wanted to add some of our research, even if they are ongoing. And just to tell you, to show you the broad spectrum on what we are involved on. So my name is Elena Mauri. I'm in the MAUS, Mobile Autonomous Oceanographic System, that involves drifters, floats, and gliders. And this is our web page where you can follow our instrument in real time. I want to spend just a couple of seconds here talking about EGO. EGO was set, let's say, in the middle of the 2000s as a European Glider Observatory. So a group that was trying to gather people and trying to enhance the activity with gliders and trying to solve together problems that would arise in using this instrument. Couple of years ago, it was changed to Everyone Glider Observatory, where the group enlarged, including many other scientists outside Europe, like US, Canada, Brazil, Australia, and China, and others. So at the moment, the idea of being together is really to try to focalize all our activities in the same way, in the trying, first of all, to be more homogenized for the data, for the standards, the same data formats available in real time. And this is the web page for the EGO group, where you can find also the meeting. Once a year we meet, and this year will be in Rockwell in the US, the first time outside Europe. Here is a slide that reassumes all the activity of the gliders in the Med. As you can see, there are many institutes that use the gliders. Now we have 33 gliders, Slocums, gliders, and Sea Explorers, sprays working in the Mediterranean Sea. Here you can see all the tracks run from the different institutions. We are mainly focusing the south part of the Adriatic, sometimes also in the Mediterranean, in the North Adriatic, and here south of Cyprus. But let's go straight to the OGS activities. As I said before, we focus mainly in the south part of the Adriatic. We perform 2 campaigns a year, one in fall and one in winter, We started in 2013 and still ongoing. And we also cover this area. Just one, I want to mention that we have 2 slocums and 2 sea gliders. The payload is like the one you are using in Mexico. So essentially we have temperature, salinity, oxygen, fluorescence, fluorescence of dissolved organic matter, and backscattering. The other area that we cover is the south of Cyprus. We performed 3 missions, one in 2009 and later, more later in 2016, 17, and 18, in 2 different projects. One was an ONR funded project with the University of Cyprus, and in 2018 and the next year, we perform another missions again in a bilateral project funded by our Ministry of Foreign Affairs, like yours. Here you have our website where you can follow all our missions. The data arrives in real time. We have we are DAC, so we perform a real-time quality control, and then we send all the data to Coriolis database. Okay, the South Adriatic, here you, here you have all the cruises, all the missions we performed here in the South Adriatic. In this picture, you can see how the Adriatic is very shallow in the north and the central part, while here in the pit we reach 1,200 meters. Everybody already told you about the Adriatic circulation, but I want to mention once more that the waters comes from Otranto, goes north toward along the Croatian coast. It recirculates a couple of times. Sometimes in the north is formed deep water, the North Adriatic deep water that goes down along the Italian coast in the deep. But there is also a coastal surface current, it's called WAC, is less salty, is mainly fed by the rivers, especially Po River that's in here. Very important is also the circulation in the Ionian that in a way condition what kind of water, if it's more salty or less salty, gets in the basin. Here you have all the data set of the South Adriatic. As you can see, when we watched the first time all the data set, we were struck by the double salinity maxima in a certain campaigns. Usually in the South Adriatic you have the lever, so the most salty water is stays in between 150 and 500 meters, like in this case. But in 2015, because the pre-convex is before the year 2016, and then in 16 again in pre-convex 17, we found this double salinity maxima. I had just added the last cruises, the last missions, but essentially the work we have done is on the first 6 missions, and these are pretty much the same, just they are plotted against the distance from the coast from Bari, because this is one way. In the previous data you saw the full data set of the mission. But now we just took the piece of data that goes from Bari to Dubrovnik, and again you can see this double salinity maxima. But you can see also this blob of lower salinity. So when we first started a look at the data, we decided that to go first to see what the historical data were, and if the double salinity maxima was present. And we found only few profiles with less accentuated salinity maxima. Here on the left, you have the mean of the campaigns, the glider campaigns, and on the right side, you have the historical data. So to start to understand what was going on, we went through the data, the flow data that were deployed in the pit. And since the pit is very deep, the float tends to stay in the same area. So what you can see here is that the time series can start from 2012 to the end of 2016. You can see that at the beginning, let's say in 2012, there is a big amount of salt coming in the basin. Then there is this black line is the mixed layer in the winter of 2013. It's very deep. It goes down to 700 meters. Then we can see the intrusion of this very unsalty water or less salty water that stays for a very long time, because 2014 was a very mild winter and we didn't have a strong deep convection. It was only to 40 meters. And the very the low salty water stayed more than 12 months in the area. Then at the beginning of 2015, we have a deeper, just a little bit deeper convection until 250 meters. And this intrusion of water, of less salty water. Again, in 2015 and 2016, there is an intrusion of salty water almost at the surface, subsurface layer. So the thing that seems a little bit weird, even if you have a mixing here, you have a very low salinity nucleus here. We went through the precipitation, the data of the water river discharge, what we essentially think is that, as you can see before, or you have seen before, this nucleus of low salty water can help to dilute that in this period of time, in 2015, this nucleus of water, and dilute and bring, since it's lighter, brings down the mass of salty water in here. At the end of 2016, we have a deep water convection up to more than 700 meters, and that mixed everything and canceled the double eddy, the double salinity maximum, sorry. We were not sure that the float will give all the information throughout the basin, so we took slices of a layer between 0 and 40 meters throughout the different years from 2013 to 2016. And what we can see is that at the end of fall 2013, there is an increase of a lowering of salinity at that layer, and the low salinity covered the full basin at that depth. And again, then it started rising again the salinity. Here's just to show you that the amount of, there were not big peaks of, this is pore river discharge, but they were for a long time. So that the years characterized by low salinity at surface was really a year with a lot of pore river discharge. I just want to show you a few more examples of what we did. For example, here we, in 2013, May 2013, we performed this mission along the coast, and here is the slope of the pit, and you can see that here we caught the cascading.
So which were the parameters you were showing?
Salinity, it was density here, the red one, oxygen, salinity, and temperature. Another experiment we performed again with the water, the dense water formation. It was with the Croatian people. Now in front of the Kvarner channel, where you have seen that the bora is blowing quite hard, strong, and we performed the mission here in front, where is a temperature front, and what we got is this. Essentially, we can see a very strong front, very sharp, and it goes right to the bottom. It's very shallow. It's a shallow area because the slopes gliders we have, they can mount both shallow pumps in front or deep pumps, so we're using in both conditions. These data were used together with the ADCPs that they were the Croatian put on the bottom of the channel. They were used in a model, in the Aladdin model. It's a ROMS model, to understand if that area is an area of deep water, dense water formation. Because the idea is that also there can be produced this water, but the both model and observation agrees is that the water is definitely formed, deep water is definitely formed over there, but it's not as deep as you can get the water in the center of the basin. There is it's deeper than the basin outside the Gulf of Trieste and the area in front of the Po. So the water is produced. It has a 20 days residence time, so it will be remixed, and the water gets out, especially in the south part of the Kvarner Bay. You have an inversion. Usually, during the strong Bora wind, the outflow is in the south, while usually it's on the north part of the channel. Okay, so. I added, after we were talking yesterday, you were talking, Miguel, you were talking about the eddies. I added another couple of slides showing you what we are doing in the Levantine. This is a project, CINEL is a project funded by ONR. It was done in conjunction with the University of Cyprus, and we performed 5 different campaigns. These campaigns, 3 in the fall and 2 in the winters. Here you have a cartoon of what is going on in this area. As you can see, it's a very dynamical area where you have the current along the coast getting in this way and then going all around in an anti-clockwise sense, and you have a lot of eddies of different characteristics. Some are anticyclones, some other are cyclones. What we did, we took the ADT and we did the mean on the time of the project between September 2016 to August 2017. And what we got is that the Cypress eddy is the main dominant feature in the basin, while the other features, the other eddies, they start and they can disappear, they can merge, and so they have a lifetime that's quite short. While the Cypress eddy is pretty much always there. What I did. I'm sorry. What I did here is that I took I did an off-molar diagram of the longitude of the cypress in one direction and one in longitude and in latitude. And what you can get is that the eddy in September, October, November, December, it can get very wide. It can be like you can see here. I put some examples. It can join the North Shikmona gyre, and it stays for a long time, for 3 months. Then it detaches. It becomes big and smaller, disappears just for a little bit, and it moves around. Like as you can see, also in latitude, it moves around. So we were not happy about that. So we used the glider, the drifter tracks. Here you have the full data set for the mission, for the entire project, and we took the data only. These data are related only when we have at least 3 drifters, and we wanted to compute the radius, the speed, at least for these 3 months. It comes from February to May 2017. And so here you have the graph of the radius versus the speed, and you can see that the maximum speed is more than 5 centimeters per second, and it reaches at 40 kilometers, and then it goes down. So essentially, what you can get is that the radius of the eddy is 40 kilometers, but we want also to measure that the movement of the eddy, and so we did a regression again. And we finally came out with a number, 150 meters per day, is moving southeast. It's pretty much what we get from the altimetry. But we also realized that it's not a completely circular, so it's a lenticular, and so the period it can go from 5 to 10 days. It depends on where you have the drifter. You can trace. We traced for the entire year this eddy and the other eddies using SSTs overlaid, and on top of them there is the geostrophical current derived from ADTs. So it's a quite. We have a quite good degrees with drifters, the ADTs, and the temperature fields. Obviously, the temperature fields is not the real one. Just to take off the seasonal cycle, we took it off the mean, and we divided by the standard deviation. So you can really compare all the images throughout the period. So if you are wondering what you see when you cross that eddy with the glider, here it is. We cross the glider 5 times in fall, and as you can see here, these are salinity, color coded. The black lines are the density, the white are the oxygen. We displayed against the latitude, but can be very close to the distance from a certain point, because as you can see here, the tracks are oriented this way. So what you can get is very different features. You can get that the eddy is not circular, is really asymmetric, as you can see here. It depends obviously where you cut it. It's across it. Obviously, it's difficult to predict because the altimetry is giving you a good idea where it is, but it's not as precise as you would like to have it. Anyway, but you can also see that in some cases like this, the density, you see the doming down here. In this case, you have a doming down, but also one up. And you can see this salty water mass entrapped in the middle of the eddy. So we are still trying to come up with a solution because it's quite complex. I wanted to show you also the other parameters that we measured in the eddy, and you can see that this is oxygen, but here you can also see chlorophyll. That's straight around 100 meters. So we are talking about October, and the backscattering at two different wavelengths because this is an old glider and so has a little bit different sensor. But you can see that inside the eddy, you have a very low backscattering also here. This is one, but this is also another example where you can see the oxygen overlaid in white, and you can see the lower backscattering right below. So I wanted to show you this data because we are struggling to come up with something. I was thinking that it was nice to have a way to talk about that. And this is the same eddy, but in winter. And so you can see the completely different situation. You can have a higher salinity or very homogenized in the center. And don't pay attention to the bottom because we measure until 400. So this one, it's just because we sample at the beginning and the end to calibrate the oxygen. So it was made this way. And pretty much it. This is what I wanted to show you what we are doing. And thanks for listening.
Thanks, Elena. I have questions. Vedrana? Yeah.
Hello, just curious, that warm core that you find in the side of the jar. Salty.
Yeah.
Okay, sorry. Salty.
Yes.
Is this in a particular period of the year only, or?
Yeah, we found it in October. It was in October. There are a few ideas why is there. It has a similar salinity than the lid, the layer below. Sorry. It can be entrained by the fact that at that time the eddy was very wide and took also the non-Shikmona jar and can entrain maybe water masses coming from a different places. After the mixing, the winter mixing, you have the full mixing and it disappears.
But you have lower salinity on when you have the mixed over there?
This one?
Because I can see the numbers
Okay.
are less
The
than the other
maximum is 39.2
and the other one?
and the other ones is again 39.2, so it's a little bit lower.
That the other one or this one?
No, this one that has the same scale.
Oh, it's the same
Yeah,
color.
it's really difficult to say.
Yeah, it's not the same that we see over there.
So when I mean the eddy was there when you started your sampling, or when did it form the eddy? When was the genesis? Because it's very important to understand this bulge of salinity to see if it's a current that entrains some salinity core before the formation of the eddy.
Yes.
Or it's a part of a current that it's bending, or it's like some instability of a current that forms an eddy and traps the salinity core, like the loop current that it's a Yucatan current with a salinity core and then bends and detach.
It doesn't, I didn't have the time to show you. We went through as you have seen, the ADTs and the currents fields on top through the full year before the experiment, and we couldn't see any current entrained by the AD. The only thing that we see, but is something absolutely it doesn't help to explain. There is in September there is a mid-Mediterranean jet that comes here, and it's a very strong current in this direction. But here, usually you have a small eddies that dances around, creating some form, and they are not as strong as this one. So this is a good idea. I will go back and look, but the currents over there, like you said, it's very difficult to see them to be entrained. There is only one occasion, by chance, probably is this. There is an upwelling, just one case, but it's in November. It's really at the same time we were sampling here in front of the Israeli coast. But even with the upwelling that we saw, because there was a wind blowing for 20 days coming from, let's say, east, more pretty much from the east, and the water was brought up, but it's very cold. I mean, it's cold and not as salty at the surface. So it's there were also modelers trying to understand why, but we still didn't get the.
Because you did not check like a movie or long term like ADT to see how it forms, or
I did
how
that.
it evolves, to understand a little bit.
I did that. Most of the time you have it really lenticular. It's a table here, a little bit lenticular. Only once, like I showed you before, and train the other eddy that's in here, and that's it. But when the eddy was entraining also the other eddy, we were already there. So probably it was formed before, and I haven't seen this the year before. I haven't seen this creation of the big, huge eddy. But I will go back, but I think it has to be formed after the previous deep convection. I mean, deep convection, let's say. So it means from March, it's already summer over there, or late the spring. So you have few months, 6 months possibility to see the creation of that. But it's a good idea. I'll go back
and ultimately every
definitely.
day. Yeah, just checking how it looks like it's stationary, but no, I guess not.
It moves like I showed you before, just a little bit. It depends.
Westwards.
Obviously, it's southeast, but just for that 3 months, as you could see, it dances around a little bit. So, but anyway, I went through more than 2 years altimetry, and I went through and see movies but I couldn't get anything. Thanks a lot.
Thank you, Elena.
Thank you.
Thank you. So we have now change a little bit. I will give the floor to Roberto and Sara. And okay. This is tu vuoi sederti qua? Sì. No, perché devi stare. No, perché
Non si vede.
ok. Ok.
Good afternoon, everybody. So we are changing also in some cases the basin, so we are not working essentially in the Adriatic, but in the Ligurian Sea, which is on the other side of the Italian peninsula, but more or less, of course, the processing techniques are to be applied in all over the world. So the subject of my talk is the use of active and passive acoustics in order to monitor different parameters or processes in the ocean. As we all know, sound waves propagate for a long distance in the ocean, and the water acoustics is the science which studies this propagation, propagation in the water column, the interaction with the boundary of the water column, so the sea bottom and the sea surface, but also the different processes which have something to do with this kind of propagation and interact with the propagation. We can divide underwater acoustics in two big classes: passive acoustics, in which we are essentially interested in listening to the sound, specifically at some particular frequency or for some specific purposes, and active acoustics, in which we have a transducer which emits sound pulses, and another transducer which collects the echo or collects the sound. It can be the same of the transducer generating the sound in case of monostatic systems, or another completely different transducer in case of bistatic systems. Everything is ruled by the sonar equation in the active and passive formulation. So let's start with an example of the study of background sound, so the passive acoustics. We are listening to the ambient noise in the ocean with a combination of different sources that can be natural or man-made, anthropogenic. In case of natural, we can have geophysic sounds produced by geophysical sources, so wind, rain, of course, seismic events, and biological ones, so mammal vocalization, fish, crustaceans, and then so on. And of course, anthropogenic sound, essentially the ship noise, sonar activity, or seismic exploration. The primary sources for identifying the primary information in order to identify the sources of the sound is the frequency, but also the duration and the sound level have some importance. So we can work in the spectral domain in order to detect, classify, and quantify, in some cases, these processes. And you can see on the right the famous plot by Vance, in which the pressure spectral density is plotted against the frequency, and a lot of different types of processes, human activities, and so on, occupy different parts in this plot. So we are, for our business, for our work, especially interested in the RC interaction processes, just because they play a central role in exchange of heat, water, momentum, and so on. So in between the atmosphere and in the ocean. I have not to say that the network of measuring stations in the ocean are extremely sparse with respect to the land station, which collect meteorological measurements, and also remote sensing systems. Of course, the satellite does not provide generally enough time and space resolution in order to monitor some particular processes. Let's go a little bit in detail about the sound which is generated by rain. So it is essentially due to two processes: the splat, so the impact of the drops in the ocean, and also the creation of the bubble, which is remaining trapped underwater. The relative importance of these two components depend on the raindrop size, and this is the relation which links the frequency, the resonance frequency of the rain, and essentially depends on the bubble radius. We may have different types of precipitation, drizzle, which is light rains, and with raindrops, which can have a diameter less than, lower than 300 microns, or even convective downpour rain, in which the diameter can reach also half centimeter. As the drop size changes, also the sound is changing. So you can hear if it works.
It worked before.
Yeah. So this is the background noise plus some rain. So when we collect this time series, it was raining. So in order to assess the capability of revealing such surface processing using acoustics, we set up a kind of experiment in which we collect rainfall data from a meteorological network of radars. One of the radar was set in this position. This is the Ligurian region. And we have also to collect a land station collecting rainfall in order to calibrate the radar. We got ship traffic through IS in order to monitor the noise due to the ship passage. And we collect a meteorological measurement from the W1 M3A observatory that we manage. Just a few words about this platform. It is essentially constituted by a large spar buoy. It is 51 meters long, 12 tons weight, and it is almost on the middle of the route between Genoa and Corsica, 40 miles far from the coast on a deep sea bed of 1,200 meters. The last part of the acronym, so M3A, means Mediterranean Moored Multi-Sensor Array, and it is also shared with the system by OGS in the South Adriatic, and also with another system which is managed by the Greek colleagues in the Cretan Sea. So we have W1, the W1, which means Western 1. The OGS system is Easter 2, and the Greek one is Easter 1. So we have a lot of sensors installed or deployed on board our system. So for collecting measurement about meteorology, marine parameters, physical, oceanography, or biochemical, the waves, also an acidification monitoring CO2 in the atmosphere and in the water, of course, also the ambient noise package. On a separate mooring, when it is deployed, we also collect temperature, salinity, and currents. This is the operational scheme, how the system works. Again, this is a scheme which is in some way shared between all the M3A systems. So we collect the data on board the platform, we transmit the data ashore, the receiving station, we apply in an automatic way quality control procedures and deliver in standard format the data to external data centers like Coriolis or the in situ TAC of Copernicus. So we are interested in wind and precipitation for this experiment. So wind measurements are collected using a standard 2D sonic anemometer, whereas the rainfall measurements are collected by using a compact weather station, collect a lot of other meteorological parameters, but especially rainfall using a piezoelectric sensor. So essentially, it counts the drops which hit the plate on the top of the sensors. The other important thing is the so-called passive aquatic listener. This instrument was developed by the colleagues of APL, University of Washington in Seattle, US, and it was further upgraded by colleagues by HCMR, the Hellenic Center for Marine Research in Athens. It consists of a low noise wideband hydrophone, a low power microprocessor, and a signal processing board. It wakes up at pre-configured time interval, collect a short time series of the ambient sound, process this time series, essentially it makes a Fourier transform, store spectra, try to identify the sources contained in the time series, and quantify also the sound, especially for wind and rain. So it is important, it is nice to see how the data are collected. So we can see here for a period of 2 weeks, the sound pressure levels. This is a spectrogram, and you can see that the color, that means the level of the sound, is pretty much follow the black line, which is the time series of the wind speed measured by the buoy. But there are also some high frequency contents or some peaks in the spectrum which are exactly at the same time of the rain events, which are in red. So how the rain spectra modify? So we can subdivide this spectrum in different classes depending on the quantity of precipitation and also depending on the wind speed. So we use, of course, rain measurements and wind collected by the buoy. For us, in this case, this is the truth. And the spectra have been averaged depending on the different cases. There are essentially two important features that we can monitor. The first is this peak, which is characteristic of drizzle, so very light rain, which tend to increase as soon as the rain increase and also the wind speed increase, and disappears when there is heavy downpour convective rain. And the other important feature is in this part. So when we have very strong particular event rain case, rain higher than greater than 20 millimeters per hour, we have very high sound level in the low frequency band. We can select the sound pressure level at 5 kilohertz in order to perform a kind of parameterization of the rainfalls and to estimate the quantity of rain. And so in the lower plot, you can see 7 months of data. The orange plot is the rainfall measured by the buoy, and the black dot are the rainfall estimated using acoustics. One other important thing that was an original aim of our experiment was to compare the rain measurements estimated by using acoustics also with the radar. And you can see here for this event of November 2011 that the acoustic estimation of rain is even better than radar estimation, meteorological radar estimation of rain in this location. We can perform the same type of analysis for the wind. So we can consider the wind speed on the buoy, average the spectra of the sound, ambient sound, and we can see that, of course, the spectra tend to increase as soon as the wind speed increase. But when there is very high wind speed, the sound tends to be even lower with respect to other spectra with lower wind speed. So in this case, we can select the frequency of 8 kilohertz. So we can take the sound level at 8 kilohertz in order to produce a kind of parameterization, which provide us the quantitative estimate of the wind in meter per second using acoustics. When we are collecting the ambient noise, of course, we are collecting everything. So one important method in order to determine which is the primary source is to look at the stationarity of the time series. So if we have rain and wind, we have stationarity spectrum over time. When we collect such kind of noise or sound, we are not in the same condition. Just for example, we can hear some noise. So this is a whale in the Ligurian Sea, and another one. The same type of analysis can be performed also in other seas. These are time series and spectral in Antarctica. It is important to see that even in this environment, we can perform ambient noise measurements. So these are spectra of the presence of man. So kick and walk on the pack, and close or far snowcat working close to the measurement site. And we have animals, in this case, weather seals. We perform some kind of localization. And of course, the spectra can be very, very different from one sample to another. So, for example, we have ascending whistle. not so. And we have another one, which is this one. And the spectra of these two different types of signal are very, very, very different. This is the green for the ascending and the red for the descending. So it's possible to distinguish the sources. Now we can move to an example of active acoustics in order to monitoring ocean waves. So acoustic wave meter systems are based on a directional array of high-frequency altimeters, which are installed on the sea bottom or attached to fixed platform. But the W1M3 buoy is relatively stable, so we can deploy a directional array at 10 meters depth of altimeters looking upward. You can see here, and this is on the mast, and trying to collect the distance between the position of the altimeters to the water surface. There is some processing that we have to do in order to clean the signal, to remove some spikes or outlier. It is also very important in this case to perform a kind of compensation or correction for the motion of the platform. So we have to take into account the angles and the acceleration. And we have to compute the power spectrum in order to be able to estimate the wave characteristics, perform cross correlation in order to have an estimation of the wave direction. This is the formulation of the problem. So assuming that the waves are moving in are planar waves, of course this is not the truth. Having a directional array, we can use directional variable techniques in order to estimate the main or principal direction of propagation of the waves. We perform a kind of calibration validation of the system using a collocated data wave rider buoy, so it's a standard wave buoy, and you can see here the time series of our system of the wave rider and the scatter plot with a pretty higher correlation coefficient. We use this system, our system, in order to validate or to compare with a data set produced by ESA in a project which was named GlobeWave. So they produced a global, let's say, data set, putting together a lot of different missions all over the world. So we select, of course, the data around our system at different ranges, 7, 20, and 40 kilometers far from the buoy. What we have found is that the best fit is with a satellite within a radius with the distance of 40 kilometers far from the systems. The satellite significant wave age distribution show an elevated percentage of high waves, which is not so correct in our basin, but especially since in this project they put together all the satellite and made some kind of comparison and global, let's say, calibration of the satellite system. It is strange, but we perform better with uncorrected data with respect to the corrected one. This is maybe due to the fact that they corrected satellite measurement using essentially systems in the Pacific and in the Atlantic Ocean from the NOAA in the US. So I leave the floor to Sarah for the last part.
I will show you some results we obtained analyzing the acoustic data from the DCP to monitor the zooplankton migration. Although the DCP is commonly used to monitor currents and flows. Just very few words about the working principle of the DCP that are the starting point of our methods and our analysis. Sound pulses are transmitted from the transducer. The sound is reflected and or scattered when it encounters change in density, and the energy of the reflected signal can be used to estimate the amount of scatters at a certain distance from the transducer. The eco-variability is depending on the presence of suspended particles, sediments, discontinuity in the water density, fish, and also aggregates of planktonic organisms. There is a close relation between the raw scattering signal and the total volume of zooplankton biomass, just from a qualitative point of view. The adding value of using ADCP data to monitor zooplankton consists in the capability of ADCP to be autonomous and to monitor on long term and with different temporal and spatial scales. And the same long-term service cannot be performed using traditional direct means, like, for example, the WP2net. The main parameter that we use to analyze the migratory patterns is the backscatter strength. The computation of this parameter is depending on the manufacturer and also on the model of the used DCP. And although all the formulations are derived from the Sonar equation. Just for give you an idea, the RDI for the RDI broadband DCP, we can use the expression proposed by Dennis that takes into account some technical parameters of the instrument, the setup, the parameter setup chosen by the users, and also some properties of the water column, such as the acoustic absorption and the temperature. Gostio van Aren pointed out that the obtained profile can be influenced by a low signal-to-noise ratio. So they proposed a new parameterization of the term related to the the signal-to-noise ratio, and they introduced this new parameterization with a constant A that, in order to determine this constant, they propose a best linear fit between the SV values obtained by Dennis and this new expression. But this new formulation is valid only for those beams that satisfy a good signal-to-noise ratio. That means a signal-to-noise ratio greater than 10. If we use this kind of formulation, we can compare a DCP dataset from different deployments with different configuration like parking depth, beam size, and so on. We tried to, during an experiment we performed between 2003 and 2006, we deployed the same RDI Sentinel 300 kilohertz at different depth with different sampling time. But it's really interesting to notice that looking at the time series of the free period and looking at the backscatter strength at the surface at 30 meter depth and at about 70 meter depth, the SV values are very comparable each other in all the free period, although they are three separate experiments. Although based on only one frequency and without concomitant net samples, the analysis, as we saw in this workshop, the analysis of backscatter variability at different time scales allows for the identification of different zooplankton migratory patterns, and also we can infer about the presence and the composition in the area of the investigation. During the long-term glider mission for environmental characterization, which took place in the northwestern Mediterranean Sea between September and November 2017, we were able to deploy with other partners an RDI quartermaster 150 kilohertz at about 250 meters depth, with a cell size of 8 meters and one measurement every 15 minutes. If we analyze the time series of the backscatter strength, we can see very high value in the upper 100 meter from from mid-September up to mid-October, and this could be ascribed to the late bloom, the late summer bloom that is typical on the northwestern Mediterranean Sea. And it's really interesting to notice a periodicity, a very well detectable periodicity on the 24 hours that can be ascribed to the dire vertical migration. So the movement performed by several species of zooplankton, which ascend from the deep to near the surface around dusk and descend around dawn. If you compute the daily average of backscatter strength and also on the vertical speed, we can see that there is a quite perfect match between the decreasing in the backscatter strength during sunrise and the increasing during sunset. And again, if you analyze the vertical speed, we observe negative vertical speed around the sunrise and positive vertical speed around the sunset. This could be ascribed on this nocturnal or normal diel vertical migration. That is not the only pattern followed by the zooplankton. Sometimes some species exhibit a twilight migration. That means a cycle on 12 hours instead of the 24. And the powerful method to identify these two kind of pattern is the use of the time frequency analysis. If you compute the power spectra on the time series I showed before, we can see two peaks, one on the corresponding to the 24 hours and another one smaller corresponding to the 12 hours. This secondary peak is not an artifact of the transform, the Fourier transform, but is a real signal. And indeed, we are not able to find this signal at all the depths. Just for an example, if you analyze the backscatter strength at 127 meter depth, we can notice that the peak on the 12 hours is quite absent. Many marine organisms respond to the rapid change of the light level in a similar way as they respond to regular cycles of day and night. And this happens also during solar eclipse and also during a full moon with clear skies. I show you one of these examples during the full moon with clear sky and the new moon between November and December 2009. We deployed the NRDI Sentinel 300 kHz at about 150 meter depth in the Ligurian Sea with a beam size of 2 meters and one sample every 15 minutes. And if we analyze the time series, you can see that in correspondence of the full moon with many light, so light also during the night, the zooplankton seems disoriented. This seems confused of this light, and so in the vertical velocity we can see also a negative velocity at midnight and not only at 6, so at the sunrise. And also during the night we have a up and down, the movement up and down, a continuous movement up and down. Whereas when dark is present for all the night, so no light at all, we can see that there is an ascent during all the night. Positive values of vertical velocity were observed from sunset up to sunrise, the sunrise of the day after. These methods can be applied in several regions. It's not depending on the basin we are observing. And for example, we applied the same method to a time series of backscatter data acquired by an RDI narrowband in this case at 150 kHz that was deployed in the Terra Nova Bay for 1 year, from February 2000 until January 2001. And it is very interesting in this case to verify the close relationship between the backscatter strength and the annual solar cycle. If we compute the fast Fourier transform and we analyze the amplitude of the 24-hour and the 12-hour harmonics, there is a very good agreement between these values and the annual solar cycle. The diel vertical migration is very reduced or quite absent in two periods. During the polar night, with the minimum of the solar radiation, and also with the maximum of solar radiation. So these are the two periods in which we are not able to observe diel vertical migration. On the other hand, this is really detectable when the light is penetrating to the ocean just under the polar night, just at the end of the polar night, and during autumn. So in the transitional period between light and dark. Just to conclude, the combination of active and passive underwater acoustics methods could significantly contribute to the monitoring of the oceanic environment and also to a better characterization of the ocean status. The analysis of the acoustic data in the frequency domain makes possible to distinguish the different sources of ambient noise, so geological phenomena, wind, rain, biological sources, by means of their own acoustic signatures. The analysis in the time domain allows the detection of seasonal trend, interannual variability, and can be very helpful for the identification of climate changes and also for the definition of mitigation actions. And last, a reanalysis of available acoustic data time series acquired by ADCP worldwide can contribute to deepen the zooplankton knowledge, especially from the migratory patterns, although the experiment might have been conceived for other types of studies. Thanks for your attention.
Thank you, Sarah. Do you have any questions regarding?
On the wind, on the wind with the sound, no? What is exactly hearing the instrument? It's hearing the white capping, because the wind is generating waves and the white capping.
The process that generated the sound is the white capping, so the wave breaking.
The wave breaking.
So the density essentially of the bubbles,
Okay.
which resonate, which have a frequency of resonance frequency. So we hear this kind of noise or sound.
And the orbitals of the this you can hear. Huh?
No. It is not so, let's say, precise. Also, it was written in the slide. Also, the direction, of course, of the wind is possible to estimate. So the direction, different direction makes some kind of different direction of the same wind speed makes the same sound, of course.
And the comparison was pretty good, no, with the wind on the buoy.
Yeah.
It was pretty good.
Yeah,
And it's
those
at 10
are
meters from the surface. You compare with the wind at 10 meters above the
Yes,
surface.
we have the meteorological package between 10 and 11 meters above the mean sea level.
But so if you have wind and rain together, how you can distinguish?
From the acoustic point of view,
Yes.
there is a multivariate classification algorithm. Okay, so now we are working to improve this classification. So with, for example, with neural networks or other type of new modern classification scheme. But up to now, it is essentially based on the comparison. It's a kind of binary decision tree. So you have to compare the sound at some frequency with some threshold. It's a method that needs to be in some way calibrated on different sites where you are able to deploy the instrument. So it's not generally possible to deploy an instrument with a closed configuration of different. It's better to test or to try to have a kind of very preliminary verification. You have to train in some way the classifier.
Because the environmental noise is depending side by side. Yes. So you have to.
Yeah, the background noise.
Otherwise, you cannot,
Yes, you cannot use the same thresholds.
It's actually based on threshold, so it's on the level.
Any further question? If not, we pass. Yeah.
If the sky is a cloud, you can.
We are
see
not
the
able,
difference?
no, you are not able to see the difference, for sure. We analyze this data also without clear skies, but without clear skies, the scatterer seem to have the normal behavior without any confusion.
The second question is, I understood during the polar night,
Yeah.
you have no difference in light in
Dial vertical migration, yes.
I can understand during the transition season
Yeah.
that you have the maximum. But during the summer,
During the
After summer, in this
Yeah.
case, the position of the sun changes during the night, during the day, and so you can not see minimal vertical migration, not very high,
le altre
but
slide,
a
scusate,
minimum.
le altre slide me le hai messe?
You
Con le
have
altre due,
extra
yes, no,
slides
I
just
prepared,
for
okay,
the
I prepared this one, perfect. Okay. Just to show you what happens. The gray line is the clear sky solar radiation, the theoretical clear sky solar radiation, and the green is the best strength at 32 meters, the red one is 80 meters, and the blue one is 160 meters. This is at the end of the polar night, where we have the absolute minimum of the signal at 160 meters, exactly match the light maximum. When the lines are shorter than lasting 5 to 10 hours, there is again a good correspondence, and the zooplankton seems to remain near the surface. Then we have the austral summer. During the austral summer, there is the solar radiation is maximum. The light was present also at the night. So we have not this change night and day. The daily cycle in the upper level is more evident.
The temperature during the day is changing.
Yes, okay.
During the night,
temperature, yes.
The light is
Yes,
not
but the light
same.
is present. So if we use as driven only the light, this is the situation. So we have a reduce in dial vertical migration in the deeper level and more variability in the upper. When in autumn, for example, we notice a semi-diurnal cycle, so 12 hours instead of the 24. And this could be ascribed to the limited food concentration that oblige the zooplankton to go up and down faster. And in winter, this is also interesting because in winter, no migratory pattern is visible, but there is a variability in the surface level. And this could be ascribed to the presence of larvae dwelling near the ice edge that can be considered like a nursery.
You are in a collinia.
Yes.
Yes, CNR. As far as we know, we are okay. And we have now the last presentation. Here, is this one. Okay.
Well, good afternoon to all. I'm Matteo Vinci from OGS and ODC. Last presentation, probably the only one so-called data manager. The bus is coming, so I will go pretty quick and I will try to be not boring. I will present how the Italian LODC links to the European networks. We will see something about data management practices and the standards adopted. An outline of the presentation, we will make a quick recap about IOC, IOD, and ODCs. Then we will see something about the group, when, who, goals. We will see something about the oceanographic data management. And then more specifically about data flows, data quality, data policy, digital object identifiers, something about our web portal, and if we have enough time, some details about a project. Well, let's see something about IOC, IOD, and ODCs. Some of you probably already know IOC is the Intergovernmental Oceanographic Commission of UNESCO, established in 1960. And is considered the only competent organization for marine sciences within the United Nations. Within IOC, there is a program, the IOD, that is the International Oceanographic Data and Information Exchange, that exists since 1961, with the purpose to enhance the marine research. How? Facilitating the exchange of oceanographic data and information between participant member states, and trying to meet the needs of the users. Inside the IODE, there are the NODCs, the National Oceanographic Data Centers, that are one of the 3 structural elements of the IODE. The NODC mission is to provide access and stewardship for the national resource of oceanographic data, gathering data, providing quality control, processing data, providing summarization, dissemination of data, and preservation of them. Since 2002, OGS became the Italian National Oceanographic Data Center, and we are quite proud of this. Let's see something about my group. We can say that there are several souls in this group, and try to describe you a bit how it is composed. We can see in the middle what is the core, that is my coordinator, and also our national representative, Renzo. Then in the right branch of the picture, we have the IT people that are dealing with the more technical stuff. Elena is a bit between the technical stuff and the content. And then in the left-hand side, there is the other group, and I'm also inside this group. And we are dealing more with the contents. Someone is dealing with contaminants, someone with litter data management, also me, and someone other with chemical and biological data. As NODC, the Italian node, our group has been involved in several projects since the 90s up to now. And in this project, there were several elements that contributed to grow, to build an infrastructure that is still existing, that is the SeaDataNet infrastructure. This infrastructure became the core of several European portals and collected information from more or less 600 European data originators. And in this organization, up to now, there are more than 100 data centers that are providing portals for several teams, like bathymetry, physics, chemistry, geology, and biology also. Let's go a bit deeper into the goals of my group. The main goal is to facilitate the exchange of the oceanographic data and information, and this is done harvesting and ingesting marine information, standardizing this information from a syntactic and semantic point of view, by doing long-term archiving of oceanographic metadata and data, following the principle of collect data once and use and reuse them, developing and applying quality procedures for metadata and for data, and developing and maintaining an Italian portal following international standards like OGC, ISO XML, and so on. Probably our main challenge is to provide a data access as open as possible to support the research activity. And as NODCs, we are providing free metadata access and data access following agreements with data originators. We will see more in detail later something better about the data policy. The challenge of oceanographic data management is a challenge of heterogeneity of information. We are dealing with several kinds of data, for example, several disciplines like physical data, chemical, biological, several matrices, water column, sediment, biota, different method of measurement, different instruments, different spatial and temporal resolution. Furthermore, we are dealing with a growing complexity with the different kind of data that we are dealing with. For example, we can start with an example from a, let's say, simple physical parameter, that is the temperature of the water column in situ measured, going to a more complex information like nutrients, in this case nitrates, where you have several information about the matrix, in which part of the matrix has been measured, and with which method has been measured, to the probably most complex kind of data that we are dealing with, the contaminants. Contaminants of a pentachlorophenol in a biota matrix in a specific part of the biological of the animal and measured with a specific kind of measurement method. Our data flow is mainly receiving information from the observatories that can be delayed mode observatories like cruises or historical data, or near real-time observatories like buoys. We make a standardization of this information, as I told you before, from a syntactic point of view for metadata and data format, and from a semantic point of view, using common vocabularies that are used to use the same terms inside of our wide community. We perform a quality check. We include our information in our database or international infrastructure, and then we forward this information and share following the needs of the different stakeholders that we are dealing with. Let's see now a bit more in detail some of the workflows that we are dealing with. For example, here we have an example of the delayed mode workflow that are data coming from example from cruises or historical data. We receive data with the data policy from the originator. We'll include, thanks to some software, this information into our database. And then we are able, thanks to other softwares, to share this information like data in web interfaces or metadata, always in web interfaces or European-wide infrastructures. Another case, here there is the workflow of the near real-time data that are coming from example from the observatories that we saw also this morning, like the Mambo buoy or the E2 and 3A from Vanessa, where data are automatically sent by, for example, from satellite or Iridium system, are obtained here in our data center as test files. Then by Java software, they are converted into a specific software that is the ONM from Open Geospatial Consortium. That is a specific standard used at European level for the sharing and the interoperability of oceanographic data. These data in observation and measurement format are included in our DB, in our database. We make a validation of this information. When the data are loaded in our database, they can be available through web services as netcdf files, for example, or they can be enriched by metadata using the sensor ML format and included in a sensor and observation server that can provide this data through the web. This kind of information are metadata of the instrument used that are principally mainly filled by my colleagues up to now. And we hope that in the near future, there are discussions about this. This information should be provided directly by the sensors, and so will be included in the automatic flow. And here another example of the newer data, we can say. For example, another kind of delayed mode workflow. And here we have the example of the litter data, a recent achievement of our data management group. We are dealing mainly with beach litter data, seafloor litter data, and floating macro litter data. For this kind of data, we made initial status of the art to understand which kind of standards were available and consolidated at European level. And based on this, we decided to adopt some kind of standards already available for beach and seafloor, while for the floating microliter, we used our standard deriving from the CDataNet community that are mainly standard based on CDIs for metadata in ODB. What is to highlight for this kind of workflow is that it's not so automatic like the previous that we saw, because are quite new data. And for example, for these two branches of the litter data, there are still no tools and not so much automatic ingestion of this kind of data. And this will have to be developed. Let's skip now to see something about the data quality, probably one of the most important points in the data management. I found a definition in the IOC manual describing the quality fundamental to ensure the data consistency within a single dataset and inside a data collection, and to ensure that the quality and errors of the data are apparent to the users who has sufficient information to access the suitability of the dataset for a specific task. The data quality is performed in our experience and in our group at different levels. First level is the metadata enrichment. So we try to answer to some basic questions that are providing you the information about where data has been achieved, when, how, what, who achieved the data. Once the data are enriched by this metadata, we start a first level check. This is done at a data center level. We are doing this in our group, for example, and we make some really simple kind of position and time check, checking that this information are realistic. We compare measurement with broad ranges and specific regional ranges already available for that kind of measurements. Whenever available, we also compare data with climatologies. And as a result of this first step of quality control, all the data are archived in our database, followed by a quality flag that provides information about the reliability of the information that we store. Then, when data are checked with the quality flag information, they are ingested in our infrastructure or database. There is also a second level check. For example, we are involved in this European project. We have some regional aggregation group. Data that are included in the infrastructure are aggregated at regional level, and further regional control are performed by some regional groups. These regional groups follow some common protocols, and if there is the need, they report to the people that submit the data. If there are errors or anomalies, the data are updated and upgraded, and in this way we perform a continuous quality feedback loop that upgrade our data quality. Why are important metadata? This slide is to show you this. For example, if you receive an information like this one, 18, you would like to know maybe who took the data, how it was taken, what is that, when was taken, where. If you are able to have this kind of information, probably you will be happier because you are able to do something with that number. For example, you can know that our data from OGS, from a CTD instrument, that is temperature of the water column, taken in 2013 in February, at that latitude and longitude, with a specific quality value, telling you if the data is considered good, bad, below detection limit, or what. This slide was mainly to show another important part of the work of providing metadata to the data that we are storing. And this is the challenge to provide a correct semantic model for the description of the parameters that are measured. Here I put the example of the, let's say, simple temperature in the water body measurement, and here the example of the contaminant in the Mytilus edulis, just to show you how these two terms has been decomposed in this semantic model, a model where a property of an object in relation to a matrix has been measured by a method. Let's go now to see something about more in detail about the data policy. As I told you before, our main challenge is to provide data access as open as possible to support the research activity. We, up to now, are providing free metadata access, and the data access following the agreements with the data originator. Why this? Because we need to keep, from one point of view, the data originator rights that want to be acknowledged for their huge work to achieve data. And from the other point of view, we want to provide open data, as open as possible, to the research community. So we make an agreement with the data originator, and we decide how the data are accessible. Our group follows as a data policy the CDataNet data policy that is based on the following principle. The data provider defines the data policy when this is not already provided by the project. And the data policy is included in the metadata that always follows the data. Here to show you which one is the percentage of the data policies in the data that we are managing up to now. You can see that for the moment, the majority of the data are licensed, so restricted, not free access. But there is a quite high number of public data. There is also another kind of data policy quite used that is academic, that means free access to people that use them for academic use. To say something more about the CDataNet data policy, we can say that all the metadata are freely accessible without any condition. And to access to the data and to products, users need to have a registration. So we are able to know who wants to use the data. This is useful, for example, to make statistics and reporting that are required by the European Commission, that are the funding agencies. And the users need to have an acceptance of additional conditions that can be requested by the different nodes of originators of data. Here you can see an overview of which data policies are available in CDataNet, from the most open one, the unrestricted, to the no access one. And about the data policy, we can say that, as I said you before, the access to all the data stored in OGS and NODC, the data policy is defined with the provider, with the data provider or by the project. And the data access restriction may change over time. For example, you can decide with the data originator to have an embargo time in which the originator maybe needs to analyze the data and make some publication, and after that embargo, the data are freely accessible. Access to data requires to restricted data. No, sorry. The access to the data requires an authentication and an interaction with the data originator in the case of restricted data. This means that the restricted data are accessible to the users, only need to be requested. Who is requesting the data needs to specify which one is the use, and this is the kind of interaction that we need to have with the data originator. Let's say still something about the DOIs. We are also providing a DOIs minting service. What are DOIs? DOIs are digital object identifiers that are quite widely used to freeze a data set and to permanently identify this data set with a specific unique code. And these are quite useful to make a citation of a specific data set inside a publication, for example, and make a really clear acknowledgement of the data provider of the data set. We have, well, about the DOIs, probably you know that is a frozen version of the data set. So the DOI, the unique identifier, is defined for a specific time and space. And our group is providing a mask where it's possible to access to these frozen datasets. We are obtaining data from the observing systems. We are elaborating them with quality control, dataset aggregation, and we are populating catalogs of metadata and data. And then we are providing some services to the users, to our stakeholders and users. Let's see something now about from our portal. And here in the specific case, there is the link to our metadata catalogs, where it's possible to access to information about cruise summary reports, that are information about the cruises, EDIMED, where are the information about specific datasets that were registered, EDIOS, that are observing systems, and EDIMER, that are information about the projects. Here we have an example about the mask to access to information about the cruises. Here another example about the metadata that are accessible through our portal, where it's possible to drill down in this information and see, for example, the data distribution through the metadata, or the disciplines where data are available, the temporal coverage, the license. And here we have the mask for the data access that is available also from our main web portal of the Institute, or from our web portal. And we are providing a mask that is providing you the chance to search by date, area, parameter, or project, and search for the available datasets. Or there is always the mask where it's possible to access to the frozen datasets from DOIs that we saw before. Still a few words about the project. I think I'm still in time. Still a few words. And this is one of our projects, is the Emonet Chemistry 1. Oh, I think it's a quite late version, okay. The Emonet Chemistry project is the European Marine Observation and Data Network, and is a project from the European Commission, based mainly on the Marine Strategy Framework Directive. That is a directive that is ambitiously aiming to obtain the good environmental status for our seas and oceans by 2020. There are several topics of this Emonet. In this picture, you can see that there are, for example, a thematic portal dealing with human activities, physics, bathymetry, biology. We are the chemical one. And we are dealing with some of the descriptors of this Marine Strategy Framework Directive, that are the descriptor 5 for eutrophication, the descriptor 8 for contaminants, 9 for seafood contaminants, and the new one that we're dealing with is the descriptor 10 for marine litter. We have a specific focus in beach litter, seafloor litter, and floating microlitter, because this is considered up to now a quite hot topic in the EU, but also in the international community over Europe. This just to show you that the work done in the data management point of view, with the metadata, the data acquisition, the quality control, just playing with the metadata led us to have an overview of which kind of information is available at European level for the litter data. For example, this is one of the preliminary results that we obtained from this work of data management on litter. In this picture is the content of our database, showing, for example, the available surveys at European level of beach litter, that are the surveys that are highlighted by the green dots, of floating microlitter, that are the green lines, and the seafloor litter, that are the red lines. And again, here, another map showing you the distribution of the surveys of the beach litter available in our database, so available up to now at European level, highlighting which kind of list has been used for the description of litter items, because you must know that at European level, up to now, there is not a single reference list used to describe the litter items present in our environment. Here we are trying to highlight the heterogeneity of these lists that are used to describe this kind of data. Some use cases that came from this data management work on litter are the European Marine Litter Single-Use Plastic Assessment. The European Commission used our data to make the single-use plastic assessment. Then the beach litter baselines and top 10 items done in collaboration with JRC. So a work that was done to highlight which are the top 10 items that were found in the European environment. And furthermore, we are contributing in the revision of the technical group on marine litter master list, that is the list used to describe the litter items at European level. Just to conclude, to highlight the benefits of the data management done, there is long-term information preservation and reliability. The data access is as open as possible and ruled by the data policy. We are following the H2020 FAIR principle for data management. These are principles at European level that are requested for each project up to now, and that are asking that data have to be findable, accessible, interoperable, and reusable. We are following the INSPIRE directive, that is the second, let's say, important directive in this period, because it's providing rules for the data management to have an interoperable European geospatial infrastructure. And the DOI's minting provides the principal investigator acknowledgement and the possibility to share the data. Thank you for that.
Thank you, Matteo. So it's very nice to know a few more things about the data management that usually we don't know too much, and also not everybody is aware to see this. Any questions?
So, for curiosity, you show a list of permissions. It's free and completely restricted. In the EU, how are the percentage of free data that we have?
I showed you before which one is the situation for the Italian part, and we have to say that the majority are still restricted data. The minority, of course, are public data. But what is good in our opinion is that data up to now are not completely free. But the data policy mechanism, in my opinion, is a good mechanism to have a trust relationship between the data providers and the data managers, so that the data providers are in some way aware that the data will not be given without asking acknowledgement and so on. And they are encouraged to share more and more data that they are producing. In my opinion, is this one the positive.
Yeah.
The data preservation, you have a protocol to do backup or these kind of things?
Well, this is not done, the protocol not at a project level, it is something that is done at group level. But of course, we have reservation through backup and copies that are, let's say, always available.
Because sometimes the space is not.
Yeah, as you probably know, we are also working at institute level now, because we are trying to decide a data policy at institutional level, at the level of OGS, and data management work for all the groups of this institute. So this will become more and more institutional, but up to now it's done only at group level, let's say. It's a decision of my group or the other groups that are working in the same project.
And all this group or team that you show, it's all these groups working on that data management?
Yes.
This is awesome. So it's a very nice budget just for data management. No?
It's quite wide.
People.
Yes.
You are preparing the way that the data will be free, no? Like the United States nowadays, it have to be like this, right? You know, have to be free. But another question, you are talking about data. For me, a numerical model, it's data too. You are completely looking for observations.
Yeah. Up to now, we are not dealing with numerical models, but we would like to enlarge also to this.
Because it's data too, no?
Yeah. I agree with you.
Terabytes and terabytes. Yeah. And how you can control the quality data for a numerical model?
This is a good question. But for example, not only for the numerical models, also not for all data types, we have so consolidated protocols for data quality. For example, for litter, There is nothing up to now. It's something growing. Yes, what I wanted to say also in the presentation is that for some topics, like more mature, more consolidated, like the physical oceanography or the geochemical oceanography, there are well-known protocols available since years and so on. But for some other topics, there is nothing.
But not even for oceanographic variables. For example, if you change on technology, also there is you need to define new standards, like for the glider data, that there is no maybe this quality control now, because it's a pretty recent, it's a decade that we're using gliders, so you can publish no matter you don't do any quality data. People accept right now, but I guess that in the following years, it's going to be like a standard for glider data.
Usually along the years, as you are saying, let's say the work on the quality is going better and better, growing. And so I think that also for data like gliders should be available more and more.
The community is already working on the metadata, on the formats, the common names for variables. I know it's a quite a long story, but we are working on that. And if you would like to come to Rutgers, you will hear about that. And all the community agreed, especially now UK, US, Europeans, and Australians are really working together to put together the same.
It is important to compare data. Yeah, and in US now, if you want to publish, they ask you to put the data on a public repository. So to be able to publish, you need to put your data in a public repository for the reviewers and other people to check. And it's pretty hard to don't do that. We have a very strong data policy that we cannot share data because it comes from the oil company. Mm-hmm. So we have to fight with the editor, the chief editor, and said, okay, it's private data. If you want, I can share the data just to validate my results, and I'm going to share with the reviewer who wants to validate my results that I show in the paper. But I cannot share with you the full data. But we have fights by email with the chief editor and blah, 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 blah.
That's the reason why we are completely stopped about this thing. You know? We don't share data with nobody because we can't. And we don't have any process to share data with the other investigator unless to give them the password to get our databases.
But because you are mainly founded by private associations or what?
By the oil.
We had, but also in our experience, there are different situations. There are, for example, the historical data of some kind of data that are freely accessible. More recent data have the embargo period, as I said you. Now with the environmental data, like the litter, the contaminants, and so on, sometimes that are the sensible data that we are trying more or less to handle, even if they need to be public because they are requested by the directives to make the environmental assessing. But it's not so easy to manage. For example, we make also some aggregations of data sets that are, in that case, that are not available to all the public, but to specific users that request for those kind of data, and they have a specific permission to access to this. For example, EEA is one of the users, the European Environmental Agency, and they are asking for specific kind of data set aggregations. They have access to that. We are trying to find some specific solution to specific stakeholders. This is more or less the way, but the trend is opening.
Okay. Any further questions? No, I think everybody is. It has been a long day, very nice, but I think they were very nice presentations, and also invite for tomorrow. Just to give it, tomorrow we will have. Brainstorming.
Yes.
I will ask everybody to join, because the more we are, we have the more ideas. We can have a huge range of arguments and to talk and to discuss. So we will start tomorrow at 9:30 a.m. And so now I think it's time to just stop and try to wait.